There are a few inputs that are required for this program that I'll explain. One is GPS position and time, which is obtained from a GPS receiver. And for simulation, it requires information on maximum acceleration, both lateral and longitudinal, and maximum redline velocity in the gear that you're running. I chose to use this Q-Star system because it's a 10 Hz receiver, and the racing software can read from the receiver and output an Excel file for my program. So imagine you're sitting in grid and you've just finished your second run. And now you want to enter the data that was just output to an Excel file from your GPS receiver. So we're going to enter that data. You'll see the plot will change with a new racing line. Enter your start and finish line approximately based on the number. In this case, the finish line is probably closer to 680, so I'll change that. This program can also rotate that grid if for whatever reason you wanted to. From course to course, you might need to change it. I'll get it back to the proper orientation. You can also enter camber for the track if you know it. These blue, wherever you see blue, those are curves. If you know that that curve has camber, you can label a number that represents the curve and the angle, and you'll see it'll turn red. And this could affect the simulation, but generally we don't know that information, so often I just leave it blank. And now we're ready to run a simulation, but before we do, we have to select our parameters. I've already mentioned these parameters. There's 4: maximum lateral g-force, acceleration g-force, which is assumed to be nonlinear. That's why there's 3 values here. They're all in g-force units. There's an example of a nonlinear acceleration curve. Your maximum deceleration g-force and your maximum redline velocity. The only one that you may know is your redline velocity. You can enter them manually, which is one approach, one way to do it, and that's just entering the data. It's not the recommended approach. Automatic is the recommended approach, and that basically takes your run data itself to calculate these maximum g-force values. The automatic method derives the parameters from the actual run, so that those parameters are calibrated to that run. In other words, they're specific to the driver, to the car, to the racing line, to track conditions, to tire pressures and temperatures, and everything else that's specific to that run. As a result, the simulation will represent the maximum velocities and the minimum runtime that could have possibly been achieved for that run based on physics. So when you compare it, your actual run with the simulation, you'll be able to determine where you nailed it and where you fell short. We can now run a simulation. It's going to ask me if the start and finish lines are correct, and they are. You'll see on the plot on the right, some data points will pop up. Those are from both the simulation and the actual run. The calibration is not correct. We'll get to that in a minute. This is called a friction circle. The friction circle is a cross plot of lateral acceleration, which is on the left is left-hand turns, the right are right-hand turns, versus longitudinal acceleration. At the bottom is deceleration, the top is acceleration. The radius of this friction circle is your maximum lateral acceleration. The blue data points are from the simulation run, and the colored data points and white points are from the actual run. Let me show you the simulation run here, highlight it. And you'll see that it sits at the extremes. So you're running, the simulation run assumes that you're running at the extremes of lateral g-force and acceleration and deceleration g-force to get your minimum runtime. The color data points and the white data points are the actual run. We can now calibrate by using the data from the actual run. First, we'll calibrate the lateral g-force. You'll see the curve move out slightly because it went up a little bit to 1.25 Gs. Deceleration, it's going to actually go down. You won't see the blue curve come down. 2.62 Gs. And then we'll do acceleration. This is going to take us a little bit longer because it's calculating a curve. And you'll see there are 3 g-force values for 20, 40, and 60 miles per hour. You can compare those with the ones that are there. Accept it. Now it's going to ask you if you want to merge that data in, because it actually builds a database as it's going also of some of your best acceleration values. I'm going to say no in this case. But I don't know if you noticed, it went slightly up. It moved slightly. So now that we have this calibrated, we can actually go in now and look at our results. You see several plots here. The plot in the upper left is a plot of the racing line. The different colors, I'll explain in a moment, represent where I lost velocity and lost time and why. The A is at any point in time is the actual position of my car, and the S would be at that same point in time the position of the simulation. The curve in the middle compares the last run, the previous run, with this run where it's green. My velocity is greater in this run than the last one, than the previous one, and where it's red, my velocity is slower. This is your friction circle. Same as you saw before. Again, this has an A and an S. They're a little bit different. A is the actual location on the friction circle of the car, of the actual run, and the S is where it should be. In other words, it's the simulation run at that same location. The curve on the bottom, there are actually 2 curves. The blue is from the simulation run, and the white is from the actual run. It's up there, cross plots of velocity versus time. On the left is the starting line, and the right is the finish line. The gap between these 2 curves represents the loss in velocity, or translates into a loss of time. The colors give the cause for that loss. Green color represents a weak acceleration. You can see the steep slope on the simulation curve versus the rather shallow slope on the real run, and which means it translates into a loss of time. Yellow is even worse. That's where it's accelerating in the simulator and I'm decelerating, causing, again, a significant loss of time. The red is a little more difficult to see. The red is where both the simulator and the actual run are decelerating, but on the actual run, the deceleration is much steeper, much more extreme. Again, losing time. You can also adjust the sensitivity of what you're looking at here. For example, I can increase the sensitivity and show you almost every example of where I lost time, including where I'm pointing to where I shifted from first to second. Or you can look at just the most extreme cases, and so this is the more where you lost the most time in these few cases here. I usually like to look at it somewhere in between, which is where I had it before. Now I'm going to show you an example where that A actually is in a real position, and it's directly before where I lost a significant amount of velocity and coming down. And what I want you to look at is I'm going to move that position forward and look at the friction circle and notice where that A moves to. It sits on the outside of the friction circle. That's exactly where I lost traction on the actual run, which makes sense. I'm outside the friction circle. Okay, for fun, I'm going to show you a race. I'm going to show you a race between the actual run and the simulation run. I'm going to speed the video up so that it's roughly almost real time. And you can see how quickly I lose time relative to the simulation. Where you can see the color of the A, the actual position change. Where it becomes more red is where I'm losing more time or losing more ground relative to the simulation. do this as a diagnostic tool because it actually takes quite a long time because the processor on my laptop isn't that fast, but it's kind of interesting to watch.